Okay, high performance liquid chromatography, or most people call HPLC, is one of the highly advanced analytical techniques that has been significantly improved over the years. So, what is HPLC? HPLC is used to separate, identify, and also quantify components in a mixture. So, it is the main chromatography technique that has been used in most laboratories worldwide. So, this technique involves separation of a mixture of compounds using stationary phase and also mobile phase. So, what is stationary phase? It is a solid or liquid material that is packed into a column, while mobile phase is a liquid that passes through the column. So, the sample will be injected into the mobile phase and then flow through the column. So as the sample passes through the column, the components of the sample are partitioned, which is separated based on their interaction with the stationary phase and also their solubility in the mobile phase. There are a lot of industries that have used HPLC to detect and quantify components. Some of the areas are pharmaceutical, bioanalytical, food and beverage, clinical, forensic, environmental, and also drug development laboratories. HPLC also can be used in pesticide analysis to detect and quantify pesticide residues, monitor degradation, perform multi-pesticide analysis, and also support environmental and quality control studies. Next, there are a lot of HPLC types. For example, the most common one is reverse phase that also used in pesticide analysis. Other types of HPLC include normal phase HPLC, ion exchange HPLC, size exclusion HPLC, and also magnetic chromatography. Alright, so the objectives of this analysis are to determine the retention time of a standard solution, which is pesticide, and also to determine the presence and concentration of pesticide residues in fruits and vegetables using HPLC.
As for the methodology, we have sample preparation and the operation of HPLC. So first of all, we're going to touch on the sample preparation. We have cucumber, apple, cabbage, and lady's finger served as the blank sample. Every sample was homogenized and completely shredded. 50 ml of acetonitrile was added and shaken for 10 minutes. It was then mixed with 10 grams of sodium chloride. It was thoroughly shaken after adding 6 grams of NaSO4 to absorb moisture. The solution was filtered and transferred to centrifuge tubes at 5000 rpm for 6 minutes. 10 ml of acetonitrile and toluene were used to extract the solution after it had been evaporated and reduced to 5 ml. 1 ml of distilled water and 1 ml of acetonitrile were used to pre-treat the solution. 10 ml of acetonitrile was used to elute 2 ml of the extracted solution that had been put into the SPE cartridge. Acetonitrile solution was collected for further analysis. The identification and quantification of pesticides were performed using an analytical technologies 3000 series high-performance liquid chromatography HPLC system. HPLC system equipped a UV visible detector. Chromatographic separation was achieved using a C18 column, with sample injection conducted manually via the injector. The detector was interfaced with a computer for data processing and analysis. The HPLC was operated under binary gradient conditions employing a mobile phase consisting of acetonitrile and water in a 70-30 ratio. The flow rate was maintained at 0.8 ml per minute. For residual pesticides analysis, the detector wavelength was set at 254 nanometer.
Okay, here we have the HPLC validation data for the 3 pesticides. Firstly is endosulfans, secondly is chloropyrifos, and thirdly is carbendazim. This table summarizes the concentration, retention time, and peak area for each compound. Let's go through the details. Okay, first thing first is endosulfans. The concentration used was about 10 microgram that had a retention time of 2.250 minutes. The peak area recorded was about 70,602,758. This large peak area indicates a strong detection signal for the compound. Next, we go to the chlorpyrifos. Similar to the endosulfan, the concentration was the same, 10 microgram, and its irritation time was slightly longer, about 3.208 minutes, but the peak area was 7,510,881, showing a distinct and measurable presence. Okay, thirdly is the carbendazim. Again, the concentration was the same, which is 10 microgram, and irritation time was the longest, which is at the 5.050 minutes. The peak area was recorded around 3,624,293. Okay, now let's look at the qualitative data that obtained through the HPLC validation for pesticide standard. This table pesticide and retention times qualitative observation for each compound. First thing first is the endosulfan. Retention time is 2.250 minutes. It was identified using the HPLC with UV detection at 254 nanometer. The observation is a clear asymmetrical chromatographic peak was observed. The identification was confirmed by matching its retention time with a standard reference. Okay, next is the chlorpyrifos. The retention time is 3.208 minutes. A well-resolved peak was identified using HPLC with UV retention at 254 nanometer. Additional confirmation was obtained via GCMS with characteristic mass fragment. This ensures a high level of accuracy in identifying the compound. And lastly, a carbendazim. Retention time about 5.050 minutes. The chromatographic peak was efficiently separated using HPLC UV detection at also 254 nanometer that employed, and identification was confirmed by comparison with an analytical standard. Okay, next is a summary for the quantitative analysis. The concentration of all the pesticide standard was set at 10 microgram. The peak areas which indicate the intensity of detection were recorded, which is endosulfan had the largest peak area, 70,602,758, showing high detectability, which is followed by the chlorpyrifos that had moderate peak area, which is at 7,510,881. And lastly, the carbendazim that had the smallest peak, which is smallest peak area at the 3,624,293, indicating lower detectability. And for this result, demonstrate that HPLC is highly effective for separating and quantifying pesticide residues. Both qualitative and quantitative data confirm the reliability of HPLC for food safety assessment. For application and implication, this qualitative analysis confirms the presence of pesticide, while quantitative analysis ensures the pesticide levels remain within the permissible safety limits for consumer. This method is crucial for regulatory compliance and monitoring in agricultural practices. For future consideration, moving forward, we recommend including more pesticide types to broaden the scope of analysis. Additionally, enhancing HPLC's sensitivity could further improve the detection of even lower pesticide concentration. Thank you.
In the analysis of endosulfan, we can see a clear symmetrical peak which was confirmed by matching retention time with standard reference. This indicates the technique's high accuracy. From the analysis of chlorpyrifos, a well-resolved peak was identified. In the carbendazim compound, the chromatographic peak was separated efficiently and was confirmed by comparison with the analytical standard. To conclude the study, HPLC method is effective in determining pesticides in fruits and vegetables due to its precise and quick identification of a variety of natural and synthetic compounds. Fundamentally, HPLC is a significantly improved version of column chromatography. Solvent is externally driven through a column at high pressures rather than solely relying on gravity. This greatly speeds up the chromatographic procedure. With growing concerns regarding pesticide in agricultural produce, this method signified the advancement in analytical chemistry.